And yeah, let's transition to the next talk, which will be given by Áron Selmeci. Sorry if I mispronounced that.
It's Áron Selmeci.
Hi. Yeah, and you will talk about time-dependent and sustainability analysis of oxygen extraction from lunar Regulus by the FFC process. Take it away.
Yes. Can you see my screen?
Yes, but you are not in full screen mode.
Okay,
no.
Good.
Yeah, perfect.
Perfect. So, dear audience, I am Áron Selmeci, working at the European Space Agency as tech with Beth Lomax and Alexander Maurice on the optimization of this experimentation setup plant. And yes, the topic of today, this presentation is the time dependence and the insustainability analysis of the FFC process for oxygen extraction. We optimize this process for in-situ resource utilization for space exploration, therefore enabling sustainable long-term exploration for extraterrestrial objects. The aim of the process to utilize the readily available resources for extraction or manufacture the following materials: like water or oxygen for breathable air for astronauts or rocket fuels, or using the regolith metals itself for additive manufacturing like buildings or spare part components. As we have seen many times in these presentations before, the FFC process was originally designed for metal production on the Earth for metal powder. And therefore, we have an electrochemical cell with molten calcium chloride salt. And during the electrolysis, the metal oxide is reduced into metal, and the oxide anions migrate to the anode, where they form carbon dioxide or carbon monoxide in case of carbon anode, or oxygen gas in case of inert anode. We also add calcium oxide to the salt because this material can increase the ion conductivity of the salt, and also it incorporates in the metal oxide and therefore changing the mechanism of the reduction. In our experiments, we use lunar Mara regolith simulants, which is mainly composed of silicon dioxide, aluminum oxide, and magnesium oxide, and pyroxene and glass-rich basalt crystal phases. The lunar Mara simulant in general has more diversity in crystallic phases than other simulants like the lunar high-glanz simulants, which we can benefit from. So if we see that we can reduce the lunar Mara regolith simulant efficiently with the FFC process, then we can expect that other kind of, let's say, all kind of simulants or regoliths from all area of the moon could be reused. In the next slide, you can see a sketch of our experimental setup, as have been shown David as well before. In our experiments, we have a tubular reactor, which has a cooling circle at the top, and at the bottom there is the aluminum crucible with the molten salt electrolyte, a sintered regolith pellet in a cathode, stainless steel cathode basket with Inconel rods, and carbon, in our case, carbon anode used as an electrode. We use inert argon gas to purge out the evolving gases through the electrolysis, and we analyze these gases with mass spectrometry. In the FFC process, many parameters can change, or we can change it directly, or it changes during the electrolysis. This can be the initial calcium oxide content of the electrolyte, the duration of the electrolysis, cathode anode distance, surface area of the anode, the composition of the anode material, electrolyte composition, or other parameters like the temperature or the voltage. In our experiments here, we changed the duration of the electrolysis, and we used carbon anodes because the focus of the experiments was the change of the composition in the electrolyte and the structure of the regolith. So therefore, the carbon anode doesn't influence these results. It doesn't contaminate the salt. And also, it's a very well-known anode material from previous scientific studies, mainly for metal production. We do analyze our experimental results with simple analysis like measuring mass yields or visual inspection, but we use also titration to analyze the composition of the electrolyte. We dissolve the samples in hydrochloric acids, which reacts with the calcium oxide content, and we measure the remaining hydrochloric acid content with sodium hydroxide. We use mass spectrometry to analyze the evolving gases, where the mass spectrometer ionizing, separating, and detecting different molecules, and from the amount of the carbon monoxide, carbon dioxide, and oxygen gas, we drive an indirect relation to the oxide content of the reduced regolith. And we also measure directly the oxygen content of the reduced regolith with inert gas fusion technique, where the regolith powder sample is placed in a graphite crucible, and on hot temperature, we extract out the oxygen from the powder with the carbon from the graphite crucible. The effluent carbon monoxide converted to carbon dioxide and detected with infrared spectrometry. And here you can see some results from the experiments for the progression characteristics of oxygen extraction. As you can see in the first diagram, the oxygen, the state of the oxygen, the extracted oxygen from the data derived from the gas analysis and from the oxygen measurement of the solid product. We can see that it's stably increasing as the duration of the electrolysis is going on, but at some point the rate of the extraction is dropping, as you can see in the second diagram as well. And this also can be observed in the drop of the current efficiency in the third diagram. Therefore, we can see that for efficient oxygen extraction, the electrolysis should be stopped before the full reduction of the regolith. However, we should consider here, let's say, sustainability concerns as well, like for the reuse for the utilization of the byproduct for, let's say, additive manufacturing or metal fuels. And also should point out about the experimental results that here the trends you can see in the three diagrams are related to the state of the oxygen extraction and not the time of the experiment or the electrolysis. In the next slide, you can see the theoretical change of the calcium oxide content or the oxide content in the regolith and the electrolyte. There were many studies conducted before, carried out before for the analysis of the metal oxide reduction to metal powder, as the FFC process was originally designed for. And here you can see that the calcium oxide first incorporates in the metal oxide, and as the electrolysis is progressing, it's slowly releasing from the solid material, and therefore we expect an inverse proportional relation in case of the salt, the electrolyte. Therefore, first the calcium oxide content is decreasing and later it's increasing. Because this mechanism is very well established and proven, we expect that in case of the regolith, which is composed from mixed metal oxides, we expect we would have similar mechanism for the reduction. However, we wouldn't expect that for the same for all the metal oxides. In our experimental results for the reduction progression of calcium oxide content and its effect on the regolith simulant and reusability of electrolyte, we could see similar trends for the change of the calcium oxide content. In the beginning of the experiments, the calcium oxide content calcium oxide incorporated from the molten salt electrolyte into the regolith pellet, regolith sinter pellet, and as the electrolysis was slowly progressing, it released the calcium oxide content. You can see this in the form of the reduced or partially reduced regolith pellets as well. In the beginning, it's more powderish form as when the calcium oxide doesn't incorporate too much, but later it's getting more stiff, rigid, and then toward the end of the experiments, as the calcium oxide content is releasing, it's getting back its powderish form again. We can see similar trends from the mass yield. First, during the first period of the experiments, the mass yield is increasing as the calcium oxide content incorporates and slowly decreasing toward the end of the experiments. Here, we can derive let's say, considerations for the reusability of the calcium chloride salt, because if we stop the electrolysis process too early, then the calcium oxide stays incorporated in the regolith powder pellet, and there we lose calcium oxide content from the salt. So if we want to reuse the salt again in another experiment, we have to add extra calcium oxide. But if we stop the electrolysis process after the full reduction, then we get higher calcium oxide content than we need. And there, in the next, in recycling the salt, in the next electrolysis, the calcium oxide can precipitate in the pores of the sintered regolith and can decrease the efficiency of the reduction. Moreover, it's not sure that the calcium oxide content is increasing in salt at after the full reduction, because the used technique, the titration, cannot differentiate between metal content and oxide content. Therefore, it's possible that the reduced metals are dissolving into the salt, or maybe the salt can decompose as well, and we're producing calcium metals through electrolysis. Both of them are detrimental for reusing the salt or recycling the salt, because they are increasing the conductivity of the electrolytes, giving possibilities for short currents, and also can cause the contamination can cause parasitic currents in recycling the salt. To sum up, we have seen that for the most efficient oxygen extraction, the full reduction of the regolith is not favorable. However, we have to consider that how sustainable to use partially reused regolith for additive manufacturing or as metal fuels. And we also have to consider where we stop the electrolysis process in terms of retaining the optimal calcium oxide content of the electrolytes to reuse it later. Our aims for further experiments to understand deeper reusability of the salt, to carry out experiments and analyzing the change of the composition of the recycled salt in terms of elemental analysis and deeper analysis than the current experiments. Thank you for your attention.
Thank you very much, Áron. Perfectly on time, and we have time for questions.
Okay.
I don't see any in the chat right now. You can also just raise your hands if you have any questions. And there's the timer. So.
Oh, great. Perfect.
Yeah, I don't.
Nobody asking a question. Maybe I can ask not a question, really, just a thought.
Sure.
So Áron, great talk. It's very clear. I was just thinking while you were speaking, that what happens to chlorine? I mean, you showed a lot of graphs about how calcium oxide was changing, and it wasn't clear how much calcium oxide was coming from salt, how much could have come from regolith. So that's clear. But if something else is happening to the chlorine content of the salt, you know?
Yes, it can happen. We use mass spectrometry to analyze, let's say, evolving chlorine gas or evolving hydrochloric acid gas. But in our experience, the measured chlorine content was really small, which we can say that maybe because of we produce a low amount of chlorine, but also it can come from the effect that in corrosion process with the reactor itself, we can lose it. So I wouldn't say for sure that we don't produce chlorine really in our experiments, but apparently so far our experiments didn't show much chlorine production, which maybe implicates that the decomposition of the salt is not a serious challenge here. Yes, it needs a deeper analysis, it needs a proper gas and particle separation system, because from the purging out the evolving gases with the argon gas can float particles as well, and there it's not an easy way to find a proper filtration system which doesn't react, let's say, or absorbs the evolving gases and enable them to be analyzed by the mass spectrometry.
Thanks. I see there is another question and a hand up, so I will switch off.
David has his hand up, so very quick, David.
Yeah, thanks, Áron, for your presentation. shame we never met in person. I promised when I'm back from holiday we will.
Okay.
My question is, do you have any thoughts on how you clean the salt after the use? So you identified sort of a dirtiness now in the salt. Do you have any thoughts on how you might clean it up before the next run?
Yes, the current process of the salt cleaning, let's say first consider when we use it one time, it's quite dirty, the top layer, because there we have floating carbon particles or carbon even patches, and other contaminations coming from the reaction with the electrodes and anode and similar products. But if we remove the first layer, then we can obtain a relatively clean salt deeper. However, we can't avoid floating particles which are coming off, for example, from the regolith pellet itself. So now, kind of a way to clean the salt, to maybe to scrap off the top layer. That's a way. It's not really clean and not really automatized or any other not developed in other way. But that's a way to avoid contaminations or to remove it. Yes, so that's a way I can see now. Or another way, what we can do to pre-electrolyze the salt, but that's changing, for example, the calcium oxide content, and that's not an easy solution to implement.
Okay, thank you very much, Áron.